Okay, now we're going to start talking a little bit about what's going on with those protons and electrons inside the atom. And we're going to need to understand a little bit of this to make sense of some of the stuff that's coming up. So I just wanted to tell you a few things about positive and negative charges. They're attracted to each other. I think you've heard this before, right? Positives attract, opposites attract, likes repel, and that is true with charges. We call this thing electrostatic attraction. It is true not only that opposite charges are like one another, but also how big the charge is and how close the charges are has an effect on this. So if I have a positive and a negative charge, they will be more attracted to each other if they're closer than if they're farther apart. So, and this is, kind of like magnets. Magnets are another thing that's an attractive system, like electrostatics. So the closer they are, the stronger the attraction. Also, if I have a stronger charge, for instance, if instead of having a plus charge and a minus charge, I have a +2 charge, so it's a bigger charge, it has double the amount of positive charge and a negative charge, they will be more attracted to each other than just a single positive charge and a single negative charge. So this is sort of something that's going to happen. We're going to sort of bring this to bear on what it's going to be analogous to in the atom in a bit. So it is true, we sort of already discussed that the electrons are in this outer portion, but they're in more of a structure than just the outer portion. They're at different distances from the nucleus. And in fact, we're going to call the regions that the electrons are in orbitals. So they're going to be identified by level and sublevel. See if I can get a laser pointer on here. So we're going to talk about orbitals, and that's where the electrons are going to be located. It's fairly complex. They're not specific regions. They're more about cloudy regions, but we're just going to call them orbitals. We label those different orbitals. There's many different orbitals in any given atom, and we label them in a couple of ways. First, we label them by level, and levels are numbered 1, 2, 3, 4, 5, 6, 7. And the level has something to do with how close they are to the nucleus. So level 1 is closest to the nucleus, level 2 is a little further out, level 3 is farther out yet. So when we're talking about the level of the orbital, that's telling us something about its distance from the nucleus. And again, we then have sublevels that are all at the same level, but there are different types of orbitals at the same distance, and we're going to talk about them as S, P, D, or F. So there's 4 different types that we're going to deal with, and each level, it turns out, only has some of these sublevels. For instance, at level 1, there's only one type of sublevel, and that's the S sublevel. Each sublevel holds a different quantity, has a different quantity of orbitals. So I might have 1 of type S and 3 of type P. Each individual orbital can hold 2 electrons. And I know that this is complex. So let's get into a little bit of these details, and I promise that I'll make it simplify it a little bit later on down the road. So level 1 has just one sublevel, S. And sublevel S's come in just one orbital. So I will have only one orbital at level 1, and is an S-type orbital. And each orbital holds 2 electrons, so level 1 can hold 2 electrons in total. Level 2 has 2 different kinds of sublevels. It has an S sublevel and a P sublevel. But the P sublevels always come in sets of 3 orbitals. So I'll have a total of 4 orbitals at level 2. I'll have 1 2s orbital, and I'll have 3 2p orbitals. So the S orbital, the 2s orbital holds 2 electrons. Each of the 3p orbitals holds 2 electrons for a total of 6 electrons. And all total in level 2, I can hold 8 electrons. Level 3 has 3 different sublevels, S, P, and D. And sublevel D comes in sets of 5 orbitals. So I have 1 3s orbital that holds 2 electrons, 3 3p orbitals that each hold 2 electrons for a total of 6 electrons, and 5 3d orbitals that each hold 2 electrons for a total of 10 electrons. The fact that they can hold them, I'm pointing out, watch out, later on when we're writing electron configuration, the order in which they put things in different ones can change. But all told, when it's completely full, level 3 can hold 18 electrons in total. Level 4 has 4 sublevels, S, P, D, and F. F sublevels come in sets of 7 orbitals. So we have one 4s orbital that can hold 2 electrons, 3 4p orbitals, each holding 2 for a total of 6 electrons. 5 4d orbitals, each holding 2 electrons for a total of 10 electrons. And 7 4f orbitals, each holding 2 electrons for a total of 14 electrons. So in theory, level 4 can hold 32 electrons in total. It turns out the order in which we fill these things, it's almost impossible. You generally never see 4f even being occupied. We're not going to put electrons there. Even though they're there, they're rooms, they're left empty. Level 5 and 6 get similar to level 4. It starts getting more complex, and we're not really going to get that far along, so we're okay. So I am warning you, soon, and maybe you've seen this already in high school chemistry, we're going to use this information and write electron configurations, and we're going to find out where the electrons are, which orbitals they're in a given electron. And just because the orbitals exist doesn't mean that they all occupy one level before occupying orbitals at a different level. We don't get to make up the rules, the atoms make up the rules, and the electrons occupy the lower energy orbitals, but the energy of an orbital depends on both its level and sublevel. And so they fill in a very unusual way, and we'll talk about that next. Okay, so just to sort of tell you, again, we've been describing these orbitals. We can think of these orbitals as different seats, within a stadium. So I have different sections, I have different levels, I have all sorts of different possibilities of places you can sit in a stadium. And again, the levels, we talked about the levels, are sort of how far they are from the nucleus. In this case, we have ones that are sort of right on the floor. We have the next section is a little further out, and then we have the final section. And also within each level, we have different types, right? We have our green sections, we have our yellow sections, we have our blue sections. Similarly, we have S type, we have P type, we have F type, and there's not even the same amount. We have a lot of green, but only a few yellow. Similarly, we only have 1 type S, we have 3 of type P, we have 5 of type D. So it's a bit like stadium seating. And just like stadium seating, it's not like all seats are created equal. Some seats are better than others, and perhaps you'd rather move up to a higher level and be in the upper level than to be right on the corner of the field. So maybe say I'd rather be on the 50-yard line in the blue section in level 2 than on level 1. And so we see that type of thing happen in the Okay, so if I put all of these orbitals we've just been talking about in order from lowest to highest energy, I've kind of moved them from left to right too, but I want you thinking vertically. The lowest energy level orbital is the 1s orbital. This here in parentheses is telling you it can hold a total of 2 electrons. The next one up is the 2s. And then from there I go up in energy to the 2p orbitals. Again, there's 3 of them, so they can hold a total of 6. My next higher energy is 3s. So far this is following a nice pattern. 1s, 2s, 2p, 3s, 3p. However, at this point, the 4s energy level is actually lower in energy. The 4s orbital is lower in energy than the 3d. So after it finishes filling the 3p orbitals, it's going to start filling 4s orbitals. After it's done filling 4s orbitals, then it's going to go fill the 3d levels. Next comes 4p is higher in energy. Again, here we go. After the 4p, notice that the 5s is lower in energy, is in between the 4p and the 4d. So after it finishes filling the 4p level, it's going to start filling the 5s level and then move back to filling the 4d level. After the 4d level, we move on to the 5p level, then it fills the 6s level, then the 5d level, and up to the 6p level. Good news, I'm only going to make you do up to 6s electron configurations. Again, notice that when I'm writing this down, the first number is talking about the level. The second type letter is talking about the sublevel. And then in the parentheses, I'm writing how many electrons it can hold in total, if I have all of them available. Okay, so when I want to write an electron configuration, I need to determine which orbitals the electrons are in, where they are within an atom. So if I want to see where is everybody sitting in the atom, I want to see where are all the electrons in an atom. And we do know that in general, they're going to fill the orbitals from lowest energy to highest energy. In general, when we go buying things, we tend to buy the ones that cost the least, and when they're all out, then we move up to the higher priced ones. That's sort of an analogy. Okay, again, we need to first figure out how many electrons there are in the atom. We can do this. We know if we know the atomic number of the atom, and it's an atom and it's neutral, we know it has the same number of electrons as protons. Oh, this is not correct. They do not have the same number of protons and neutrons. It should be same number of protons and electrons. Oops, typo there. Cross that out. This should read electrons. Okay, and then we're going to fill the orbitals with electrons, starting with the lowest energy orbital until we run out of electrons. Again, I want to write the orbitals in order from lowest energy to highest energy, and then I'm going to use a subscript to put how many electrons are in there. So this means that in rubidium, which has 37 electrons, the first two, we're going to put 2 electrons in the lowest energy orbital, which is the 1s orbital, and that has 2 electrons. We move up to the next higher energy orbital, which is 2s, so I have put 2s, it has 2. When I move up to the next one's 2p orbital, remember there's 3 quantity of p orbitals, so it can hold a total quantity of 6. 3s, 2, 3p, 6, and here's where I have to watch out. I don't move up to the 3d orbital yet. The 4s is lower in energy than the 3d, so down I'm going to fill the 4s. So 4s 2, 3d 10, 4p at 6, 5s 1. And if I add these all up, 2 and 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2 is 20, plus 10 is 30, plus 6 is 36, plus 1 is 37. I get the total number of electrons that I have. Here is a different way that I can show the same problem. I can show it based on that earlier slide that I showed where I had them in. I can just fill them in. I have 37 electrons, and I can start putting them in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37. And then when I'm finished doing that, I can just write it down. I start by looking at what I have. I have 1s has 2 in it, 1s2. The 2s orbital has 2 in it, 2s2. The 2p orbital has 6 in it. The 3s orbital has 2 in it. The 3p orbital has 6 in it. Then comes the 4s orbital with 2 in it. 3d has 10. 4p has 6. 5s has 1. And I can get my electron configuration by using this diagram. I've provided in the notes, there's a blank version of this. So if you want to print this and do it this way, this is fine. As long as you can get your electron configurations done, I'm happy. If this helps you, use it. Okay. Now that we've seen all that, it turns out that an element's location on the periodic table, it relates to how many electrons are in each level. So this is related to the electron configuration. And if I can learn to read the periodic table, I can save myself some work. Some people have trouble doing this, can't see the pattern, and they'd rather do it the long way. That's fine. Either way will get you. But notice that the periods of the periodic table, period 1, period 2, period 3, generally correspond to the level. See, I have level 1 is the reds. This is level 1. This is level 2. Level 3 is mostly in period 3, 1, 2, 3, 4, 5, 6, 7, 8. But notice it's also the purple section of the next period. Same thing with level 4. Level 4 is here, here, and here. And level 5 is here, here, here. Actually, it's here, 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 and here. So in other words, and the other thing to notice is that these first two groups are representing the S sublevel. The purple groups are representing the D sublevel. The green groups here are representing the P sublevel. And way down here at the bottom of the table, this is representing the F sublevel. And again, remember where this red line is. Essentially, this part down here should be inserted in here. So when I look at, for instance, zirconium, it is in the 5th period, 1, 2, 3, 4, 5. It is in the D block, so it is going to be filling a D sublevel. And the number, since it's in the 5th period, but D sublevels are 1 lower, it's going to be in the 4D sublevel. So that's 1 lower in number than the period. For D's and for F's, it would be 2 lower, but we won't deal with F sublevels. So I can a page where this is sort of corresponding to the electron configurations. Hydrogen is 1s1. Over here we have the weirdo helium is 1s2 over here. But notice my orange ones are, the left column is going to be s1, but it's going to be increasing in the level number. For the group 2, they're all going to be s2, but increasing in group number. For what we call the transition metals in the drop-down section of the table, those are the D block elements. Notice that it's D1, all of group 3 is going to be D1. The level will be changing, and notice that the level 3 is 1 lower than the period number. So this one's 4D, and it's in the 5th period. So 3D1, group 4 is 3D2, etc., all the way up to 3D10. Over here in the green section, these are representing the P sublevels. Group 13 is all going to be P1 elements. However, notice the level is changing as I go down the table. And the level in this case is equal to the period number. Group 14 is P2. And they're increasing in levels, and the levels correspond to the period. And we continue on P3, P4, P5, P6. So if I say, what is the electron configuration of ruthenium right here, I know the last unfilled orbital of the configuration is 46. Everything below that in energy will be filled. And so I can just kind of look at the last one of each one. So here's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and which one was I talking about? Ruthenium, 4d6 would be. So I can sort of write my electron configuration simply from looking at the periodic table if you would like. A lot of people find that's much faster. Also, we will refer to things in the transition metal area as being D block elements. Over here on the right, we will refer to the elements, the nonmetals over here on the right as and some of these are metals, some of these are nonmetals. But these elements are the P block elements, and we refer to our alkali metal and alkaline earth metal groups as being the S block elements. Okay, so again, as we just said, we call each period of the table by the blocks based on the orbitals those elements can occupy partially. So here's some questions, try them, and then I'll post the answers.